Welcome to the second video regarding the computation of Fick diffusivities for hydrogen mixtures for underground hydrogen storage applications. In this video, I will discuss how to calculate Fick diffusion coefficients for hydrogen carbon dioxide mixtures. My previous video covered an introduction into why I'm conducting these public lectures. The idea was that anybody looking at these videos can reproduce the thermodynamic data for hydrogen-related mixtures. We then moved on to learning some of the basics for MD simulations. Thereafter, we installed LAMPs. We built a version of LAMPs, a serial version of LAMPs. Finally, we solved one example where I showed you step by step to build a simulation box in LAMPs, initialize the positions of 75 hydrogen molecules, conduct an NPT simulation such that the pressure equilibrates to 50 megapascals and temperature of 323.15 Kelvin. Finally, the densities were then compared to the RefProp database, and we recovered excellent agreement. Thus, if you followed my previous lecture, you should be now able to compute densities for simple systems, such as a system containing pure hydrogen. Today, I wish to cover some basics of mass transport in multi-component systems. Specifically, I'm looking at one binary gas-liquid mixture. The key aspects of mass transport are the Maxwell-Stefan diffusion and Fick diffusion, which describe how molecules collectively transport when you have multi-component mixtures. The main goal of this lecture would be to then show you how Fick diffusions or Fick diffusivities can be computed from MD simulations. Once again, I will go through step by step and show you how in LAMPs you can calculate the Fick diffusivity for an equimolar mixture of hydrogen and carbon dioxide at 50 megapascal and 323.15 Kelvin. Unlike the previous example, where we calculated densities, for the computation of Fick diffusivity, we will be using the microcanonical ensemble or the NVE ensemble. The key references for today's lecture are the textbook by Taylor and Krishna called Multi-Component Mass Transfer. This book comprehensively deals with all the types of multi-component mass transfer, specifically the Maxwell-Stefan diffusion coefficients and the Fick diffusion coefficients and the relation between them. The algorithms to calculate the correlations and diffusion coefficients are primarily found in Frenkel and Smith and also in Allen and Tildesley. Other references pertaining to specific topics will be mentioned along the way. First, let's pick up the topic of Fick diffusion for a binary mixture. Imagine a situation as shown in this particular setup. On the left-hand side, you have molecules or blue dumbbells, which are predominantly enriched. On the right-hand side, you have another set of molecules that are predominantly enriched. If I calculate the mole fraction of the blue molecules in this left compartment, that is equal to 1. However, the mole fraction of the black molecules in the left compartment is 0. It is vice versa for the right compartment, where the black molecules have a mole fraction 1 and the blue molecules have a mole fraction 0. When you set up such a simulation, or when you set up such a system, you're basically setting up a gradient in the mole fraction. Here, x1 is the mole fraction, which is nothing but the moles of component 1 divided by the total number of moles. Similarly, the mole fraction component 2 is the number of moles of 2 divided by the total number of moles. So, what Fick's law tells is that when you have a gradient in concentration, then there is mass transport from the left to right. Now, if I calculated the total number of molecules that crossed this dashed line per unit area of this area started by this dashed line per unit time, we call that as the flux J1, and that equals minus Ct, which is the total molar concentration expressed in units of mole per meter cube, times the Fick diffusion coefficient, which has the units of meter square per second, times the gradient in the mole fraction of component 1, which is dimensionless. The way you calculate Ct, or the total concentration, is the summation of Ci, where I equals 1 and 2, since we only have two components, and that equals the density of component 1 divided by the molar mass of component 1 plus the density of component 2 divided by the molar mass of component 2. What this tells me is that if the gradient in the mole fraction of component 1 is non-zero, then you will have a mass flux which is non-zero, called J1 of C. Now, for a binary mixture, the sum of the fluxes should equal 0. The sum of the fluxes for component 1 and component 2 should equal 0. Alternatively, I can look at another framework called the Maxwell-Stefan framework. What the Maxwell-Stefan framework does is that it describes diffusion in terms of the gradient in chemical potential. It is well known that for phase equilibrium, the chemical potential of component 1 in either of the phases should be exactly equal. Thus, it is intuitive then that a gradient in the chemical potential will affect mass transfer. So, in other words, you can think of the gradient in chemical potential as a driving force. Now, the gradient in chemical potential can be written as the derivative of the chemical potential, which is mu1 over dz, which is the distance in space. Here we are considering a single coordinate or a single direction. The units of the chemical potential is joules per mole because we are looking at 1 mole of component 1. That equals RT times the mole fraction of component 2, which is x2, times the relative velocity of component 1 with respect to component 2 divided by the dms term, which we call as the Maxwell-Stefan diffusion coefficient. What is important to note here is that this equation describes a balance between the driving force, which is the chemical potential gradient, with the drag force experienced by component 1 while diffusing in component 2. Now, intuitively, if a blue molecule is trying to intrude into this right half of this box, then it will face resistance by the black molecules within that box. This resistance that the blue molecule faces is directly proportional to the relative velocity with respect to the black molecules. If the relative velocity is high, which means that the blue molecules is traveling extremely fast, then it's going to face a higher resistance. It is also intuitive that if you have more number of the black molecules, then the resistance faced by the blue molecule while intruding into this half of the box is also higher. This is precisely what the Maxwell-Stefan diffusion equation predicts. In this context, then the DMS, or the Maxwell-Stefan diffusion coefficient, can be thought of as an inverse of a drag coefficient. Now, as for Fick diffusion, if we wish to express the flux of species 1 in terms of the chemical potential gradient, it can be represented by the following equation. As you can see, the key point to notice here is that the J1 of C is no longer directly proportional to the gradient in the mole fraction, but is directly proportional to the gradient in the chemical potential. What is also important to note is that it's directly proportional to the mole fraction of component 1. This is intuitive as the flux will increase if you have more amount of component 1. Now, the flux that we described using the framework of Fick and through the framework of Maxwell-Stefan should be identical because you're looking at the exact same process and the exact same flux. It should not matter in which framework you're actually calculating the flux. Thus, you can now equate the flux that was calculated with regards to the gradient in the concentration to the flux that was calculated or expressed as a gradient of the chemical potential. The resulting equation is as shown here. Now, upon rearranging the terms, the Fick diffusion coefficient can be expressed in terms of the Maxwell-Stefan diffusion coefficient which has these following set of parameters that connect the two. Now, these parameters can be clumped together to call them as the thermodynamic correction factor or the thermodynamic factor for diffusion. The physical significance of the thermodynamic factor of diffusion is that it accounts for the non-ideality of the mixture. Thus, we now have an equation which connects the Fick diffusion coefficient to the Maxwell-Stefan diffusion coefficient. Now, an obvious question would be, why do we have two different frameworks to describe the same process? So is diffusion driven by the chemical potential, or is diffusion driven by the gradient in concentration? The answer to this question is that diffusion is actually driven by gradients in chemical potential. To demonstrate this, consider the very famous experiment by Duncan and Tour, who studied the diffusion of a ternary mixture consisting of hydrogen, carbon dioxide, and nitrogen in the year 1962. The experimental setup is very simple. You have two bulbs, bulb A and bulb B. And the initial composition of the gases in bulb A are shown here. And similarly, the initial compositions of bulb B are shown here. Now, there is a stopcock which stops the gases from mixing at time t less than 0. At time t equal to 0, the stopcock here was removed, and which allowed the gases to mix together. What is important to notice here is that the gradient in the mole fraction of hydrogen was positive for bulb A and bulb B. The mole fraction for nitrogen, however, was very small. As you can see, bulb A contained a mole fraction of 0.501, whereas the mole fraction of nitrogen in bulb B was 0.499. Finally, the mole fraction of CO2 in bulb A was 0.499, whereas it was 0 in bulb B. Now, if one looks at the experimental results for how the concentration developed for each of the components as a function of time, the plot looks as so. On the x-axis, you have the time plotted in terms of hours, and on the y-axis, you have the mole fraction of the individual components of this ternary mixture for both the bulbs. What is clearly evident is that hydrogen in bulb A increases in time, as you can see by this slowly rising curve. Similarly, one would expect that if the concentration of hydrogen is increasing in bulb A, it should decrease in bulb B, which is what is seen here. And this fits according to the Fick diffusion, which states that there's a flux of mass in proportion to the concentration gradient. A similar description can also be extended for CO2. As you can see, the CO2 in bulb A decreases as most of the CO2 is then diffusing towards bulb B. where the concentration of CO2 or the mole fraction of CO2 is increasing. This is once again in accordance with the Fick description of mass flux directly proportional to the concentration gradient. Now, what would happen, or what would one expect for nitrogen? Given that the gradient in concentration is extremely small, the flux of nitrogen from bulb A to bulb B should be very small. Now, what was observed in the experiment was surprising. What happened was that the nitrogen concentration in bulb A was not just constant, but rather it first decreased up till a time t1, and then it started to increase and slowly plateau towards an equilibrium concentration. Now, the flat dashed lines that are shown here are the predictions if one only took into account what was predicted from Fick's law. Thus, this is a clear violation of the Fick's law, which also tells you that it is insufficient to look at mass transfer only in terms of the gradient of the mole fraction. Rather, one has to account for the gradient in the chemical potential to consider the complete mass transfer picture. Now, what exactly is happening from a physical point of view? The friction between the hydrogen and nitrogen is quite high, which means that when hydrogen is being transferred from bulb B to bulb A, nitrogen is also being dragged along with it. Thus, there's a cooperative effect between hydrogen and nitrogen, which contributes towards the mass transfer. Thus, there's a clear coupling between the motion of the different molecules. A very clear explanation of this phenomena can be found in the article called Uphill Diffusion in Multi-Component Mixtures by Rajamani Krishna in the Chemical Society Reviews paper. I strongly urge you to go through this paper and look at the lucid explanation provided for this particular process. Thus, the key take-home point here is that gradients in chemical potential are the most important descriptors for mass transport. Now that we have a basic idea of how to connect Fick diffusivities in how to connect Fick diffusivities to Maxwell-Stefan diffusivities, let us try to see how Fick diffusivities can be calculated in molecular dynamics simulations. Note that Fick diffusivities are usually measured in experiments, as concentration gradients are easy to measure. Gradients in chemical potential are extremely difficult or almost impossible to measure in experiments. Thus, this is the prime reason why experimental data is reported in terms of Fick diffusivities. Now, the Fick diffusion coefficients in molecular simulations can be calculated by an indirect route where we first calculate the Maxwell-Stefan diffusion coefficients and thermodynamic factors, as suggested by the equation that I showed in a few slides earlier. Once the Maxwell-Stefan diffusivity and the thermodynamic factors are calculated, the product of the two is then the Fick diffusion coefficient, which depends on the pressure, the temperature, and the mixture composition. Thus, the first step is to calculate Maxwell-Stefan diffusivities. To calculate Maxwell-Stefan diffusivities, the key component is to calculate cross correlations in displacements of molecules of species 1 and 2, since we are talking about binary mixtures here. The first step in the calculation of these cross correlations is called the Onsager coefficients, represented by the symbol lambda. Lambda ik equals the limit t tending to infinity of the time derivative of this expression here. The first bracket tells you what is the displacement of molecule 1 in a time t with reference to time 0. The second bracket tells you what is the displacement of molecule 2 of type 2, basically, in a time delta t. The cross correlation of this product in the long time limit with their derivative gives you the Onsager coefficients. Once the Onsager coefficients are calculated for species 1 and species 1, species 2 and species 2, and species 1 and 2, they can be combined together to then give you the Maxwell-Stefan diffusivity. Next, we need the thermodynamic correction factor or the thermodynamic factors for diffusion. Let us revisit the expression for the thermodynamic factor that I showed a few slides back. The thermodynamic factor is given by the expression 1 over RT, the gradient in the chemical potential over the gradient in the logarithm of mole fraction 1. Now, the chemical potential of component 1 is given by this expression here, which is the chemical potential at a standard state, mu10 plus RT, the universal gas constant, times the absolute temperature, times the natural logarithm of the activity coefficient times x1. Now, when x1 tends to 1, which means that the mixture is completely of type 1 molecules, then the product gamma 1 x1 tends towards 1, which essentially leaves this term to drop out of this expression, which then gives you that the chemical potential 1 equals the pure component chemical potential. Now, plugging the equation for the chemical potential of component 1 into the equation here, we can derive that the expression for the thermodynamic factor equals 1 plus the partial derivative of the logarithm of the activity of component 1 divided by the partial derivative of the logarithm of mole fraction 1 at a given pressure and temperature. Now, to calculate then the thermodynamic factor, it is important that you have an expression for the activity coefficient. Activity coefficients can be calculated in many ways, and one of the standard ways of calculating them is by using the Gibbs excess energy from models such as regular Margulis Funlar models. These expressions are dealt with detail in the textbook by Krishna and Taylor. Suppose we consider Margulis model, then the logarithm of the activity of component 1 is given by this expression, which is equal to q1 minus 2q. Similarly, the logarithm of activity of component 2 equals q2 minus 2q. Here q is the Gibbs excess energy, which is a function of the mole fraction of component 1 and component 2, normalized by the product of the gas constant times the temperature. According to the Margulis model, one assumes that the normalized Gibbs excess energy has a quadratic dependence on x1 and x2 and can be represented in the following form, where a12 and a21 are free parameters. Q1 is the first derivative of Q, or the Gibbs excess energy, with respect to the mole fraction of component 1. This partial derivative is taken with the condition that x2 is unchanged. Q2 is the partial derivative of Q with respect to the mole fraction of component 2 while keeping the mole fraction of component 1 the same. Plugging these expressions into the equation for the thermodynamic factor, one can derive that the thermodynamic factor equals this particular expression as shown here. Note that the thermodynamic factor depends on the mole fraction of component 1 and the constants A21 and A12. It is not a function of x2, at least explicitly, since x2 can be expressed in terms of x1 because this is a binary mixture. Be reminded that the thermodynamic factor can be calculated directly as well using molecular simulations, and the references are available in the description provided later on. So thus, one can also use activity coefficient models like I have shown now, and one can also use direct means to calculate the thermodynamic factors. The benefits and the disadvantages of doing these are clearly mentioned in the reference or the textbook by Krishna and Taylor on multi-component mass transfer. Please have a look there. Now, as an example of how these thermodynamic factors actually look like, or a physical meaning of the thermodynamic factors, we pick the example of methanol and a mixture of N-hexane. So this binary mixture has a particular free energy that is plotted in figure A. Now, the free energy has been plotted for various different temperatures from 260 Kelvin to 320 Kelvin and is plotted as a function of the mole fraction of methanol. Now, let us pick a particular curve. Say, for example, the curve for 310 Kelvin. Given that this curve is continuous, we can extract the first derivatives or the first order derivatives of the Gibbs free energy with respect to the mole fraction of methanol at each mole fraction. The resulting plot is shown in figure B, where you can trace the first derivative of the Gibbs free energy as a function of the mole fraction of methanol at 310 Kelvin. Now you can repeat this exercise for many different temperatures. Now, drawing a horizontal line at 0 on the y-axis equal to 0 will give you a collection or a locus of points which tell you the points or the compositions where the first derivative of the Gibbs free energy equals 0. And this particular curve is then called the binodal curve, the green color curve that you see here. You can do a similar exercise. You can once again pick the curve at 310 Kelvin, and instead of calculating the first derivative, you can also calculate the second derivatives at each mole fraction of methanol for a given temperature. The result of one such exercise is shown in C. Now, you can repeat the exercise for many different temperatures. Finally, you can draw a dashed line at the y-axis equal to 0, which corresponds to the second derivative of the Gibbs free energy with respect to the mole fraction of methanol equal to 0, indicating inflection points. The collection of all such points when plotted on this plot in D gives you then the spinodal curve. What this plot essentially tells you is that if you're within the region of the spinodal curve, then your mixture phase separates. If you prepare your system in between the binodal and the spinodal curve, you're in a metastable region. In contrast, if you prepare your system outside the binodal, then you have a stable mixture. What consequence does this have on your thermodynamic factor? Now, looking at the exact same figure, we see that the thermodynamic factor inside the spinodal dome is less than 0 or negative. This implication then means that your Fick diffusion coefficients are also negative inside the spinodal dome. On the other hand, if you look at the region outside the spinodal dome or outside the binodal dome, your thermodynamic factors are positive and they have a Fick diffusivity that is greater than 0. So this roughly tells you how the thermodynamic factors of mixtures are connected to the Gibbs excess free energies. In essence, the thermodynamic factors are roughly or a great deal dependent on the second derivative of the Gibbs free energies. Once again, for the same mixture of methanol and N-hexane, we can see that for the region where the Fick diffusion coefficients will be 0 corresponds to the region where the thermodynamic factors are also 0. This typically happens when you lower the temperature for this particular mixture. A clearer exposition is available in the figure shown here, where the y-axis is plotted on a logarithmic axis. Now that we know how to calculate both the thermodynamic factor and the Maxwell-Stefan diffusion coefficients, we can thus calculate the Fick diffusivities by combining the two in a product. An important point to consider is when Fick diffusivities are computed in a molecular simulation, they tend to depend on the size of the box in which you're simulating the mixture. The reason for this is because of the hydrodynamic interactions which affect the way particles move or molecules move inside a simulation box. Thus, what one needs to do is to always correct for these finite size effects and calculate or correct the Fick diffusivities computed from MD simulations with these finite size effects. On the LHS of this equation, you have the Fick diffusion coefficient for an infinite system size or at thermodynamic limit, which equals the Fick diffusion calculated from MD simulations plus a correction factor, which depends on the temperature, the viscosity of the mixture, and the size of the simulation box. Note that the simulation box here is cubic, implying that all the three sizes of x, y, z should be identical. There's also an additional constant, which is 2.837297, which comes from the derivation with regards to the hydrodynamic interactions. Please read references 1 and 2 for a detailed explanation and a discussion regarding finite size effects for Fick diffusion coefficients. Just like how finite size effects affect Fick diffusivities, finite size corrections also affect Maxwell-Stefan diffusivities. The equation for the Maxwell-Stefan diffusion coefficient in the thermodynamic limit is shown by this equation, where the correction is given by this term here. The correction term is identical to that of the Fick diffusivity, excepting that you have an additional term 1 over gamma or 1 over the thermodynamic factor. Once again, the references for this are shown as 1 and 2, which contain a detailed explanation of how to calculate finite size effects for transport properties in molecular simulations. Now, let us move on to the input script for lamps, where I will show you an example of how Fick diffusivities are calculated using molecular simulations.